Hello everyone, thank you for connecting today to watch a webinar organized by Synopsys and Dolphin Design about Synergized Innovation integrated Bluetooth low energy radio frequencies physical layer with efficient power management. We are happy to have Hakim Jaafar, VP of Marketing and Application Lab at Dolphin Design, with more than 20 years of experience in the semiconductor industry, and also Charles Dittmer, Senior Product Manager at Synopsys, with more than 25 years of experience.
Thank you, Charlotte, and hi everyone for joining this video. As you have understood, this video is around Bluetooth low energy technology. We all know that this technology is everywhere today. We see many applications that is BLE based nowadays, and I think it's only the beginning. So the targeted audience of this webinar is anyone who is designing Bluetooth low energy product. We all know that radio could be tricky to implement, and then you have certification, regulation. And the question here is, how can I integrate and implement a robust BLE solution with its associated power management? And this is where the combination of both Synopsys and Dolphin Design makes sense. And so you will see all along this video different, I would say, scheme, different functionality, different layout that will help you to design the best low energy product of the market. Our objective is to capitalize on the strength and leverage of each company involved. Synopsys is tasked with the design and implementation of the BLE Radio PHY, the physical layer, the link layer controller, and providing a host protocol stack. This presentation will introduce the BIOS flavor of BLE radio developed by Synopsys, which offer enhanced radio performance and support numerous features available in the Bluetooth SIG standards. And Dolphin Design's role is to integrate the power management system, ensuring that your product achieves optimal performances and energy efficiency. The choice of DC to DC converters, LDOs, and their distribution and integration in the radio significantly impact the overall die size and efficiency of your wireless solution. Now Charles will introduce you the Synopsys Bluetooth Low Energy solution.
Thank you, Hakim. To give you a high-level view of Synopsys' Bluetooth Low Energy and IEEE 802.15.4 offering, let me refer to the following block diagram that you see. Our solution supports concurrent operation of both BLE or Bluetooth Low Energy and a number of 15.4 protocols. At the bottom in the diagram is our RF PHY IP, consisting of both the radio transceiver and the digital components of the PHY. Above that is the BLE link layer controller, as well as the IEEE MAC to support either Thread or Zigbee. And of course, Matter can be is IP-based. It can be run on Thread. Next is the HCI interface, or host controller interface, that's both a physical and logical interface to the host CPU within the SoC. This sits on a standard AHB or amber light interface. Above that, on the top of the diagram, is the host protocol stack that runs on the actual host CPU. For BLE, Synopsys offers a full host protocol stack and over 25 profiles and services with our relationship with Packetcraft. This BLE solution offers a single source, one-stop shop for an entire BLE solution, all the way from the antenna, all the way up to the application level that the OEM product company would design. On the 15.4 side, we partner with DSR for the Zigbee stack, what they call ZBoss, and we support Open Thread for Thread, and then the Open Matter support. These solutions are silicon proven and have been in production with leading IoT silicon providers within the industry. Diving a bit deeper into the design, you will see the three critical components to make up a wireless system. The RF PHY in the left sided box, the link layer or MAC in the center, and finally the host protocol stack on the right. For Bluetooth Low Energy, you'll see the RF PHY on the left red block, consisting of both the analog radio transceiver in blue and the digital PHY in purple. The analog radio transceiver is provided in GDS format, basically a hard macro, which is process and fab specific. We currently support both TSMC 40 ULP and ULP-EF, as well as TSMC 22 ULL. We do have additional fabs and processes on our roadmap, so please contact us. The digital portion of the RF PHY is offered in a synthesizable RTL. You do get source for this. The RF PHY has industry leading low power and performance and area, or what we call PPA, the PPA specifications, with a very tiny area and exceptional receive sensitivity while being highly integrated with virtually no external components other than a 32 megahertz crystal. This RF PHY block will be the basis for the majority of our discussions today, covering the various power topologies, and jointly with Dolphin Designs, we can offer a seamless solution. For the purposes of discussion today, we will take a deep dive into the various power supply topologies for both our 40 nanometer and 22 nanometer radio solutions. Please note, for clarity, we show bond pads in the blue boxes in the various diagrams. These are bond pads supplied in our hard macro that are wire bonded to the chip lead frame or chip pins. Conversely, the connections shown in the green circle are points that within our IP block that are internal strapping options depending on the desired radio transmit power requirements and corresponding power topologies. Now let's jump into the TSMC 40 ULP-EF solution.
Indeed, let's go deeper in each of the two solutions, 40 and 22 nanometer. We're going to go deeper and deeper. We're going to start with the TSMC 40 ULP technology solution. So on the right side, you see a nice block diagram of power management and how we could, at Dolphin Design, support analog like the radio or other controller like PCI, USB, Ethernet, other IP that, by the way, could be supplied by Synopsys. And you see here a proposal of the kind of distribution of various power management block we may have, like micro LDO or DC to DC and LDO. Let's have a closer look to the analog one. As you can see, our DC to DC is capable to directly supply the analog, which is the radio part. And you may use like a capless LDO to power a kind of DSP. It is to notice that our solution can support from 162 up to 5.5 volt. And then on the left side, you have the key features of the solution. First, the radio side, as we mentioned, provided by Synopsys, it has a very optimized silicon area, right? Including the transceiver, the I/O pad, and the matching network. And because you have the matching network inside, you may expect some bump saving on your PCB. The radio frequency cooperating is down to 0.9 volt, which make it low power, and you have an excellent BLE and 15.4 receiving sensitivity. And the maximum output powers can go up to 10 dBm. We'll see later on how we can achieve this. And then you have a low BOM cost. This radio works with only one crystal and two caps. On the power management side, the 40 nanometer offer from Dolphin Design is based on low quiescent DC to DC with a quiescence which is as much 300 nanoamp. The efficiency when the product is not very loaded, this is sometimes critical, and this is where most of the DC to DC have a very poor efficiency. Here we reach 70% of efficiency even with a very small load. And when the DC to DC is highly loaded, means you draw a lot of current from your battery because you're running processing, you're running the radio, and so on and so on. We achieve up to 85% of efficiency. We have also various LDOs like the low quiescent one named micro LDO with 160 nanoamp quiescent only, and we have fast transient and high PSRR LDO. And in the offer in 40 nanometer, you also find 32 kHz oscillator, whatever RC or crystal. And now we're going to go to the next slide here, where Charles will introduce us the TSMC 40 nanometer radio more in detail. Charles, I'll leave you the floor.
Looking at the bottom left-hand corner of the RF PHY block diagram, you will see an internal LDO. This takes a supply voltage of 1.1 volt up to 3.6 volt DC as shown in the table, and drops it down to 0.95 volts to power the internal radio components. This internal LDO is provided to ensure a clean power supply to the very sensitive radio circuitry. For this 40 nanometer solution, you will notice that we have 3 supply pins to the internal LDO. This includes VBAT, VCC, RF, and VCC analog. These 3 pins can be strapped together from an external power source. The VDDA pin is actually an output from the internal LDO taken out to the BOM pads to configure based on the desired transmit output power. As shown by the 2 green blocks in the upper left, there are 2 transmit power options that can be selected. If the standard 0 dBm TX power is desired, VDDH PA output pin and the VDDH PA input pin are strapped together on the PCB design. This offers the most power efficient design. For a maximum of 10 dBm TX power output, additional voltage must be supplied to the internal PA or power amplifier. For this option, the VDD PA output pin of the internal LDO is not required and can be left as a no connect on the PCB design. What is needed to support a 10 dBm TX power is an additional power source at 2.1 volts. While the 10 dBm is the maximum TX power in this configuration, the radio is under software control and can be set to any TX power amount that is desired. To explain both of these power topologies, I will now pass it back over to Hakim to explain how this can be achieved with Dolphin Power IP.
Here we are. Here we're going to touch really how do I connect the power management IPs from Dolphin Design to the radio from Synopsys. This is a first scenario. You will see for every single technology, 40 nanometer and 22 nanometer, we have 2 scenarios in order to provide you with the maximum flavor and different setup that you can do. First scenario is we are looking here to optimize and to reach the maximum output power with the 3.3 battery volt. So in order to do this, as mentioned by Charles previously, you will need to power your VDD HPA with a supply between 0.9 to 2.1 volt in order to support the 10 dBm. And this is what we are illustrating here with our LDO low noise. This LDO low noise is key to ensure a perfect functionality and a 10 dBm maximum output power by the radio. And then for the main supply, I would say from the radio, we recommend to plug a DC to DC low quiescent that will generate a V out from 1.1 volt up to 2.5 volt. This will address and attack directly the embedded LDO inside the radio. So thanks to this setup, DC to DC low quiescent and a dedicated LDO low noise, you can have a setup that get the maximum of this radio, which is up to 10 dBm, which is outstanding in the BLE global market. And now we have a second scenario. This one is different. This one is much more optimized, I would say, for low cost or low area. In this scenario, you're not looking anymore for a maximum output power 10 dBm, but you said, okay, 0 to 3 dBm is okay. And think about it, there are tons of applications where you don't need to have a strong, I would say, signal, either because you want to have a higher range or because your environment is noisy. If you take the example of a mouse and a keyboard, they are very close one to each other. So you don't need a high output power. You don't need a lot of energy. You don't need to go to send the data very far away. Therefore, a 0 dBm or a 3 dBm is more than enough. Or if you want to connect a lamp and you are in line of sight, you have no obstacle between your remote or your controller and the light bulb, something like this. You don't need 10 dBm. That's why the setup 0 to 3 dBm is more than okay. And for this one, you do it very simply. You just still use the DC to DC as we used it previously, but you get rid of the micro LDO, the low noise SDO we were using previously, and you tie directly the VDD PA to the VDD HPA. Thanks to this, you're going to save the LDO, reduce your die size, and still can operate the radio. And thanks to our DC to DC that supports up to 5.5 volt, you can imagine plugging directly such a device to any USB charger, lithium battery, or whatever. So here we have two scenarios we saw, up to 10 dBm, right? Or a reduced BOM and reduced size as well. The scenario where you can support 0 or 3 dBm. Now we're going to go to the 22 nanometer scenario. So let's go. As we said previously, there is also a solution for everyone who want to move from TSMC 40 and go to the 22 nanometer. Because you want to do smaller product, you want to lower the area of digital, or you want to do higher product with more flash, RAM, whatever, and you said, okay, 22 for me is my next path. So now we're going to go deep, as we did for the 40, about the 22 nanometer. Here again, like for the 40 nanometer, there are two sides of the slide. The right side, which is showing you a block diagram, a top-level block diagram, how to supply the radio, all the digital, the logic, and so on with Dolphin Design Power Management. And on the left side, we're going to see all the key features. So let's have a look to the radio. The radio has a tiny area, not because of the 22 nanometer technology, but because it has been optimized. The radio frequency cooperating is now down to 0.65. There is still an excellent BLE and 50.5 and 15.4 receiver sensitivity, and here the maximum output power has been limited to plus 6 dBm, and we'll see later on what's the impact. And you still benefit of the low BOM cost impact that this radio have on your PCB with still only one crystal and two caps. On the power management side from Dolphin, there are some change here and there. We still have a quiescent current at 300 nanoamp. The DC to DC has still a very good efficiency, actually at only 10 microamp load, and is still higher than 85% efficiency when the load is higher than 2 milliamp. The good news here is in 22 nanometer, we do have a SIMO, which is a single inductance, multiple output. If you want, it's like a DC to DC, but rather than having one input and one output, you have here one input with your single inductance, and you can generate several outputs, which going to replace somehow the use of many DC to DC. And we still have an offer in the LDO like in the 40 nanometer, and still a 32 kHz oscillator offers like in 42 nanometer. Now, let's go to have a closer look to the radio. Charles, I'll leave you the floor again.
The block diagram for the 22 ULL solution is similar to the previous 40 nanometer radio, but with a few differences. First off, the internal LDO in the bottom left-hand corner of the block diagram only has two input pins. That would be VCC RF and VCC analog. Like the 40 nanometer design, these can be supplied from the same power source. As shown in the table, minimum supply voltage is now only 0.85 volts. This is then down converted in the internal LDO to 0.65 volts to run the internal radio circuitry. Like the 40 nanometer design, VDD-PA is an output from the internal LDO, but is taken to an internal interconnect junction versus a bond wire pad out to an external pin. As seen by the three yellow boxes based on the desired maximum output power, VDD-HPA can be strapped to VDD-PA for the 0 dBm TX power mode. This again is the most efficient configuration if only a maximum of 0 dBm is desired. The remaining two configurations support either a maximum of 3 dBm or 60 dBm TX power. This is accomplished by an external source to the VDD-HPA at either 0.95 volts for 3 dBm or 1.26 volts for 6 dBm.
Like on the 40 nanometer, and you get it, we're gonna propose you here two scenarios as well, one for max output power and one for reduced output power. So let's have a look to the one of plus 6 dBm output power. As we've seen on the 40, you're gonna need a DC to DC and an LDO low noise. The LDO low noise will power the VDD HPA. This is to get the maximum output power, while the output of the low quiescent DC to DC will power the VCC NA and the VCC RF. The difference here is because you have a lower voltage digital and the output of your DC to DC now is only 0.8 to 1.4 versus the 40 nanometer, which was 1.1 to 2.5, you have a low output of the DC to DC, which is somehow compliant with the other digital power you may need inside your MCU. So in your MCU, you're going to have other digital block. They most of the time or mainly be powered around 0.8. So here you may just use a mini LDO in order to filter any noise, and then thanks to this, with the main DC to DC, address directly the rest of your digital. Thanks to this architecture and implementation here, you're going to have a more comprehensive, flexible, and efficient power management scheme. And here we are on the second scenario of the TSMC22 ULL as it was for the 40 nanometer, a much simplified power management targeted for 0 dBm output power, still supporting up to 5.5 volts battery. And thanks to this still DC to DC in 22 nanometer, and still with the mini LDO, you may have one power management unit that can both supply directly the radio and the rest of the digital on your MCU. Thanks to this, you're going to have a solution that is optimized, low area, therefore reducing the entire and the overall system, the overall die size of your system. Here we are at the end of this video, and thank you for following us through this entire presentation. As a takeaway, you see that Synopsys and Dolphin design, both together, we are a one-stop shop solution to speed up any BLE MCU design. Whether you need a 10 dBm, 6 dBm, or 0 dBm, there are solutions that exist out there. You have, thanks to this collaboration, state-of-the-art BLE performances, support for latest BLE specification. You have also the state-of-the-art power management IP block. You have DC to DC, LDO, SIMOs as we saw also. A versatile implementation. This is key to know that you have implementation that can support different different scheme. And you get the know-how and the quality in terms of IP and deliverables for both leaders in IP providing, which are Synopsys and Dolphin Design. And thank you for watching. Charles, do you want to add anything else?
Well, thank you for attending today. I hope this has been helpful. Please reach out to myself, Charles Dittmer, or Hakim at Dolphin for any additional information. Our solutions can be found on our respective websites, Dolphin/design or synopsys.com.